In the next few classes, we are going to talk about variation method, which as we will see is a very powerful approximation method and goes way beyond the scope of perturbation theory. And this variation method is completely based on what you see in the cartoon here. It is completely based on the fact that we cannot do better than the best. We are going to learn today something called the upper limit theorem, which says that no matter what you do in variation method, the energy you calculate will be a little more than, or at best case scenario, which is almost impossible to reach, equal to the ground state energy of a system. You can never get by this variation method an energy that is lower than the ground state energy. Low energy is good, right? Low energy means stabilization when we are talking about ground state. So, what we will see is that the calculated energy by this method will always be greater than, mostly greater than the ground state energy, or it will provide an upper bound for the energy. Okay. That is what allows us to have sort of a free hand with playing around the system and trying to get the correct result. This is something that we are going to demonstrate today with an example, and then we are going to prove this upper bound theorem, upper limit theorem. Right. But before that, let us not forget what we have studied. We have studied perturbation theory. For a non-degenerate state, one can represent the wave function as a wave function which is called an unperturbed wave function. This is essentially the wave function of a system which is exactly solvable. And we have studied many such examples: harmonic oscillator, rigid rotor, hydrogen atom, and then we say that the perturbation is small. So, you can write the wave function of the perturbed system as the unperturbed wave function plus a correction term. Similarly, you can write an expression for energy. Hamiltonian is written as unperturbed Hamiltonian plus lambda into V. We have talked at length about why this is a good formulation. Energy of the nth order correction is given by this integral, and we have said that we can work out even 2n plus 1th order correction. And from this expression we have actually obtained a nice expression for the perturbed wave function also. Okay. For non-degenerate states, the difference in our approach is that now you cannot really say that the perturbed wave function is some unperturbed wave function plus a correction term, because these unperturbed wave functions are all degenerate. So, you cannot say that I am taking psi k1 and not psi k3. So, first of all we form a linear combination, and then we try to look at what happens when we add a perturbation term to this linear combination of the complete set of orthonormal wave functions of the unperturbed systems that we take. And we have seen cases in which the perturbed levels are partly degenerate. We have seen cases in which the perturbed levels are completely non-degenerate starting from a degenerate level, and we have said that this has many applications in chemistry like Stark effect, Zeeman effect, d orbital splitting, and so on and so forth. For degenerate case, we have obtained at this matrix equation which gives rise to n number of secular equations, and then we can work with the secular determinant and try to find the solution. So, this is what we have studied, and perturbation theory itself is a rather strong approximation technique. The problem with perturbation theory is that its scope is rather limited. This is something that we had shown you at the beginning of our discussion of perturbation theory. It works well when the perturbed system is close to an unperturbed system whose exact solutions are known. But there are many systems which are not so easily relatable to something that is exactly solvable. There are many cases in which the deviation, if you want to call it a deviation, is definitely much more than what the scope of perturbation theory can cover. So, for such system we have this elegant method that we are going to discuss now, the variation method. Now, why is variation of what? Why is it called variational method of all things? We will see. But to start with, let us say we have an arbitrary system, and the ground state of that arbitrary system is associated with this Schrodinger wave equation H psi 0 equal to E 0 psi 0, alright. Right now we are going to talk only about ground states. So, what is the meaning of arbitrary system? The meaning of arbitrary system is that we do not know what the form of this wave function is. We have no idea. So, how do we go about handling such a system? How do we try to find out the energies of such an arbitrary system? That is what variational method allows us to do. So, we start with this thing that we know, expectation value of the ground state energy. What would that be? That would be integral psi 0 star h hat psi 0 divided by integral psi 0 star psi 0 if psi 0 is not normalized. So, this is a general expression. If psi 0 is normalized, of course, the denominator would be equal to 1, but then we work with this general expression to keep things as broad as possible. Okay. Now, what we say is we do not know what the wave function is, right, but let us make a guess. Let us assume some kind of a wave function, and that is called the trial or guess wave function. Now, at this point of time this might sound to be too much of a story. What is going on here? I do not know a wave function, but I will guess. How will I guess? You will see, we are going to, before trying to prove variation theorem, we will actually show you an elegant example where we actually know the solution, and we will see that this variation method allows us to guess a wave function that gives good enough values. So, with a little bit of experience we will be able to guess, it is not so difficult. And as you will see, these guess wave functions need not be, well, for systems where you can solve it exactly, these guess wave functions need not be exactly the same as what you are going to what you get by exact solution, but we can still get the correct energy. That is the interesting part. You do not have to do you do not have to get the right result in the right way. You can get the right result using a wave function that whose mathematical form is not the same as the exact wave function if it is possible to obtain. However, it still lets you go close to the energy, and energy, finding energy is the real problem in quantum mechanics. That is what we are worried about all the time, no matter what we do. Remember, this Hamiltonian is the energy is the quantum mechanical operator for energy. Okay. So, we start with some trial and or guess wave function, even if this sounds like very strange, please bear with me, things will fall in place in a while, not too long a while. So, we have this trial or guess wave function phi. So, what I will do is I will define this thing epsilon 0 in terms of phi, which has the same form as that of the eigenvalue of energy, right. So, if phi happen to be the correct wave function, then epsilon 0 would be the energy, right. And now let me introduce a term before I forget and then I start using it arbitrarily later on. This thing epsilon 0 is called a functional. What is a functional? A function is a function of functions, which means, see, phi is a function, is not it? Epsilon 0 is a function of functions. Depending on what phi is, value of epsilon 0 is going to change. So, energy is also a functional of the wave function psi 0. Okay? This is called a function, or sometimes it is called a super function. Okay? Super function or functional, a function of functions. For now, just the name is enough. Maybe later on we might use this in a little more elaborate manner, but for those of you who are who have a little more exposure to how quantum chemical calculations are done, you might be familiar with the term density functional theory. Okay? So, here for the first time we encounter that functional. Functional is a function of functions, epsilon 0 is a functional, it is a function of the wave function phi. Okay. Well, now hold on here, I said wave function, what is the meaning of that? Well, let us not say that, let us just say phi is a function. Okay. So, epsilon 0 is sort of the average value with respect to phi. Okay. We will see how this all falls in place. So, the upper limit theorem, which is of central importance in variational method, makes an extremely profound, important, useful statement, and that statement is this epsilon 0, which is a function of phi, has to be greater than or equal to E0, which is the actual energy of this arbitrary system. Okay. I have said a lot of things. So, let me just do an executive summary to make sure that we have all we are not left in the lurch. See, I do not know what psi 0 is, but psi 0 is the actual wave function. Even though I do not know it, it is there, right. Maybe there is some way of finding it, or maybe there is no easy way, but I do not know how to find it, and right now I do not bother, right. But energy should be measurable. I do an experiment, I should be able to find energy. So, that energy is related to the wave function like this. It is the expectation of the value of the energy integral psi 0 star h psi 0 divided by integral psi 0 star psi 0 d tau. What I am saying is, if I write a similar expression in terms of some trial guess wave function, anything, suppose the correct wave function is e to the power minus kr, and I take something like e to the power minus k dash r square, then that phi is e to the power minus k dot r square, right. And then using that and using Hamiltonian we should be able to write. Okay. Once I know the system, Hamiltonian should not be difficult to write. We might not be able to solve Schrodinger equation, we will still be able to write the Hamiltonian. So, now if I take this some guess wave function, make the Hamiltonian operate on it, left multiply by phi star, integrate over all space, divide by integral phi star phi, then I get this epsilon 0 phi. Okay. What upper limit theorem says is that this epsilon 0 phi can never be less than the ground state energy E0, and as we will discuss shortly, that opens up tremendous possibilities, and we will see how. So, the strategy of any variational calculation is this. First of all, guess a function, assume some kind of a function. How to guess a function? Well, with experience, looking at the system, thinking what the system is like, we should be able to figure out some sort of wave functions, like we are going to discuss say particle in a box in one of the later modules. You will see how we select a function which sort of makes sense on the face of it. Okay. So, start with such an arbitrary trial function, then calculate this energy. Well, when I say energy, I mean epsilon 0 phi. Then you vary the parameters of the function. Okay. If it is e to the power minus kr square, then keep on changing the value of k. What will happen? Value of energy obtained, or whatever this functional is, epsilon 0 energy like functional, that is going to change. Then calculate again. So, keep on calculating and see whether the value of this epsilon 0 is decreasing. Then continue until the value converges to some particular value, and that would be the upper limit or upper bound to this actual energy E0. Let me in spite of my poor artistic skills, let me just try to draw something and see whether I can make it a little clearer. Let us say I have this phi which is equal to e to the power minus k r to the power what will I write, q. Okay. So, let us say I am talking about phi which is dependent only on the radius vector r. Okay. Now, k is a parameter that I can play around with, q is another parameter that I can play around with. These are called variational parameters. Okay. So, what I do is I have epsilon 0 and let us say I first play around with k. Okay. maybe I will make the situation a little simple. Starting right away with 2 parameters might be a little confusing. So, I will remove this q. Okay. Let us say it is e to the power minus kr, then the only parameter that I have is k. So, I will just fix some value of k. Let us say I fix k is equal to 100 or something. Find out what is epsilon 0 phi. Okay. So, whatever it is I plot. Then I change the value of k to say 99. I find I look for the I calculate the value of epsilon 0 phi, I see that it has gone up. Then I change it to say 98 and then again I see it is going up. That means I am going in the wrong direction, because what am I looking for? I am looking for an upper bound of this value E0, right. So, if this keeps going up, that means I am not going towards E0, is not it? E0 must be down somewhere. The correct value E0 must be somewhere down here, because whatever epsilon 0 of phi I calculate, this is just the upper bound. Okay. So, those values must be more than the actual value of E0. So, I am going in the wrong direction. So, I started from say k equal to 100, I was decreasing, I went from 100 to 98 to 97 and I see that the value of this epsilon 0 functional is going up. So, I am going in the wrong direction. So, from 100 what I will do is in the next step I am going to change to say 101 and then let us say I see it goes down. That means I am going in the right direction. Change to 102, let us say it goes down, right direction. 103, 4, 5. Let us say I go from 105 to 106 and the value of epsilon 0 does not change. Okay. Maybe I have achieved convergence. Then let us say I go to 107 and the value of epsilon 0 starts rising again. What does that mean? It means that the minimum value in epsilon 0 that I have got, that is the closest I can get to the actual value of energy E0 by this variation method. Okay. Now, this diagram that I have drawn is a little too ambitious. So, what I have drawn is that I have gone almost here, that is not necessary. It is also possible that maybe I will change the color of ink. It is very highly possible and in fact that is what happens most of the time, that the minimum value that you get is nowhere close to E0. E0 you might be able to find from experiment and that is the correct value. That means that whatever trial function you have taken, that is not sufficient. You need a more complicated function. So, suppose I have started with phi equal to e to the power minus kr and I am not getting correct convergence, I am not getting convergence, okay. I mean I get it, but the result I get is very far away from experimental values of energy. Then what I do is I introduce another parameter. So, I say that phi is equal to e to the power minus k, let us say r to the power q, or I can add another exponential decay, whatever I want to do depending on what I think is correct. Now, suppose I have introduced q. Now, what will happen? For q equal to 0, no sorry, for q equal to 1 I have already got this curve, okay, by changing all the k parameters, values of the k parameter. What I can do is I can change the value of q to something else. It was 1, I can change it to 2. Okay. Let us say change it to 2 and now I get things that go down further, then I am going in the right direction. But suppose by changing 2 it went up, that means I am going in the wrong direction with q. So, what you do is you play around with q and get the best possible curve for k, see for which value of q you get. right, and that gives you the upper bound to the actual energy E0. That is what we are looking for. We can only get upper bounds, nothing else. Okay. So, now see, if I have two parameters like this, and this is a very favorite topic for many different reasons, then actually I am working in 3-dimensional space, am I not? The dependent variable is say phi. Well, the dependent variable is actually epsilon 0 of phi, that is what we are monitoring. On one axis I can have k, on the other axis I can have q, and what you get is sort of a surface. It is a horrible way to draw a surface, but I have shown you nice figures, right, of surfaces. Remember the orbitals, there we had made 3D plots, we will get something like that. Then what happens is that here I have shown you a very simple situation. I have shown you that there is only one minimum. That is not necessarily the case. More often than not, if I take, let us say I am taking a section of this surface and I am looking only at variation of phi with q, sorry, epsilon 0 with q. More often than not, this epsilon 0 with q is something like this. So, you have more than one minima. Okay. These minima that are not the deepest, they are called local minima. And this thing here is called the global minimum. Global minimum. So, what we are looking for is this. We seek to find the global minimum, because whatever epsilon 0 value that we get for the global minimum is the upper bound to the actual energy. Now, you might be a little confused here and you might be thinking, what are we doing? I mean, if you know the energy experimentally, why do we even want to bother about this system? Well, we only know the ground state energy, right. So, there are other parameters that we will get to understand. If we can explore the system quantum mechanically, we will get more information, that is the whole idea. And there are, right now we have to establish the technique. Once it is done, we might want to work with systems for which we do not have experimental values of energy also, and then we might want to do predictive theory. Okay. But right now where we have reached is this. This here is the strategy that we start with some arbitrary function which will be associated with one or more parameters. For some particular value or values of these parameters, you calculate the energy, then you play around with the parameters, you vary them. Now you see where the name variation comes from, because you are varying the parameters that are associated with the wave function. So we vary them, and every time we vary, we calculate the epsilon 0 value, and we continue until we get the lowest value of epsilon 0, the upper bound to E0. Okay. This is in a nutshell what you do in the variational method. And as we have discussed, it is essentially a minimization problem. You can say optimization problem. We seek to find the minimum in the plot of epsilon 0 with each and every parameter here. So, even though I have done a very poor job of drawing it, just imagine a surface. Okay. Imagine a 3-dimensional surface in this case, right. It will have some hills, it will have some troughs, and we are looking for the deepest trough, which is the global minimum. Okay. That is what we seek to do in variational method. So, the major players here are the parameters associated with the wave function, the variational parameters, right. So, we play around with them and we see what happens. So, that is what we will do next. We stop here now. In the next module, we will continue from here. We will talk about a specific example, that is hydrogen atom, and then we are going to derive this upper bound theorem.